Hi, everybody. Welcome to the MagNetZ. Today's seminar is by Yaochen from Chinese Academy of Science on the evolution and disappearance of paleo-West Pacific Anomaly, implication to the future of the South Atlantic Anomaly. Please, Yaochen, the floor is yours.
So, hello everyone, I'm Yaochen. I come from China, and today I'm very pleased to introduce my work to everyone here. And because this is my last year in my PhD candidate, so today I will introduce my PhD work, and it includes the West Pacific work and another recent work. And today my topic is the time dependence of the geomagnetic surface weak intensity anomaly. And okay. So today, I will give a brief introduction about the geomagnetic field, and then I will introduce two weak intensity anomaly, and one is the South Atlantic Anomaly, and another one is the Paleo-West Pacific Anomaly. So let's go to the introduction. Oh. So the Earth has a global dipole magnetic field, and this dipole field is generated by the internal dynamo. The magnetic field is strong enough to protect our living environment by blocking the high energy particle from the solar wind. And we know that, and we people have known about the Earth's magnetic field for several thousands years ago. And but during that time, the people only have a rough idea about what the magnetic field is. But after the 1840, the Gauss developed a method to measure the magnetic field intensity. That is the true beginning of the modern geomagnetic field research. Uh-oh. And after that, after we had the measurement method, and we got a lot of observation data. And here I divided this all kind of data into two different types. And one of them, I call them like direct recent observations. That means this kind of data comes from the measure the magnetic field directly by using some instrument like compass or satellites. And this kind of data has a advantage of the wide coverage and the high resolution. And another type of the data, I call them like indirect ancient or paleo observations. And this kind of data comes from the laboratory measurements of rocks or something. And that records the direction and intensity of the ancient paleomagnetic field. And this data has a lower resolution, but it can extend very, very far back in time. And when we already have this many different data, and researchers have built many different models, and each models they choose the different data and coverage and cover different time period. So here, for example, the IGRF. The most famous IGRF model, and it's called the International Geomagnetic Reference Field. And this model combines data from the satellite observatory and the survey records surround the world. And they are the recent high resolution models. But compared with these high resolution models, the ancient or the paleo models are much smoother than this recent one. So all of this model provide us with a good way to study the evolution of the geomagnetic field. And the result shows that the magnetic field are never stopped the changing. In the historical records, the magnetic field has even reversed its polarity, and the most recent reversal was the Matsuyama and Brown reversal. It's about 0.78 million years ago, and there have also has several excursion. The excursion means that the axial poles move to the low latitude and back to their pole again, and it didn't lead to the full reversal. And all of these changing characteristics are related to the non-dipole feature components. And over the past 2 centuries, the energy of the Earth's dipole field has been decreasing, and the influence of the non-dipole field becomes more obvious. So, one example of the non-dipole field on the surface is the South Atlantic Anomaly, and it's kept expansion already for more than 1 century. So some study even discuss that whether this anomaly could be the next precursor to geomagnetic reversal. So it shows that sounds like the South Atlantic Anomaly is very, very important. And so the next question is, what is the South Atlantic Anomaly? So next, let's have a look about that. So the South Atlantic Anomaly is the most important structure in the recent geomagnetic field, and the area located on the South Atlantic region. The most significant feature is that the weak surface intensity. And because it is a too weak and even like an anomaly, that's why we call that as a South Atlantic anomaly. And because of this, the weak intensity, so in this area, the protection of the geomagnetic field is reduced. And that's why in this area, the radiation level are higher than other places. And even sometimes, for example, during a very strong solar wind storm, some special space weather phenomena can occur, like the equatorial aurora in the figure, this one, the light. Sorry. So for the evolution of the SAA over the past 2 centuries, the SAA evolution has shown the following characteristic: the area expanding and the center in density keeps decreasing, and both of the center and the area shows the drift, shows the westward and the southward drift. And however, since 2010, there has been a new, very, very important detail appeared that a secondary minima has appeared in the southern east part of the SAA. So it is a very, very new and very important characteristic. And we even think that it may be marked a transfer of its evolution. It's very important mark. So my research will focus on this recent split characteristic. So for that, we will call this feature back later. And here I want to show some. I want to talk about why there is an anomaly here. So the SAA is a surface feature, as we said before. So, but beneath it, there is on the CMB, on the commental boundary, we can observe some reversal flux patches in the radial field, and it's shown as this figure. Can you see my mouse? No. The blue areas you can see here. So the study suggests that there is some reversal flux patch are caused by the thermal heterogeneities below the commental boundary, and this radial field feature are also changed by time. Okay. And here we can see that in the ancient time, the South Atlantic Anomaly, looks like a uh, re repeatedly appeared near the South Atlantic region. And for example, in this figure, in the 48,000 years ago and the 1,000 years ago, and there was an anomaly on the South Atlantic region. But why does this region often host a anomaly, and why there is often the reversal flux patch on the CMB below this area? And we also think about why it's often has an unusual heat flow in this region. And we think that it may be because there is an LSVP, is a large low shear velocity province beneath the SAA. But however, there in this figure we can see that there also is another LSVP on the Pacific part. So what's the special of the South Atlantic part, and what happened on the West Pacific part? So in my work, we try to show some characteristic of the paleo intensity time dependence in the West Pacific part. So here our research found that there is another paleo anomaly appeared on the West Pacific. So next, let's turn our attention to the Pacific part. Okay, so from the story of the SAA, we already know that the intensity anomaly are very, very important. It's like a window to the core mantle boundary and the geodynamo. But looking at the historical distribution of the intensity minima, we can see that it's not only in the South Atlantic part, and there is also another peak at the Pacific part. So we have another question is that what happened beneath the Pacific part? And in the history records, during the 17th century to the 19th centuries, there was another small-scale anomaly existed on the West Pacific part, but now it is total disappeared. And this anomaly is considered as a primary factor of the equatorial aurora recalls in the North Korea. And therefore, our work in the 2024 provide an analysis of the evolution of the WPA, of the West Pacific Anomaly, with the hoping of shedding light on the evolution of the SAA. So, for our work, we choose the model GeoFM1 and the HistCalMag, these two models, because these two models, they combine a lot of ship's log data, and this kind of data have a very good coverage on the sea, because the West Pacific anomaly and the South Atlantic anomaly are the anomaly on the sea. So we think that these two models can help us better. And for tracking the WPA, and we try to do that from two parts. And one part is find a center of the WPA, and here we choose the local minimum. And another hand is about the area. So here we try to define the WPA's area is where the intensity is lower than 36 macro Tesla with a normalized number. And the normalized number is we call it as the F ought. And we define this normalized number, try to avoid another average influence of the other region. Intensity influence of the other region. Okay. So now I try to show some result of my work. So here is the evolution of the center or the local minima. In the GeoFM1 model, the WPA first appeared in 6020 at this location. At this location, and drift westward And then in 1780, the secondary minima appeared to its east, and which continued to move eastward and with a decreasing in density. And around 1810, the primary center already disappeared, while the secondary minima in the east continued to drift to eastward. It's the center minima's evolution. And then it's about the area. And from the area evolution, we can see that at the first, the WPA expanded, and then the shape thinned out. And subsequently, the secondary minima appeared and leading to the split with the WPA into two isolated parts. And as they move into two different directions. And then finally, the primary part, the west primary part, diminished and disappeared. This is the area evolution. And we also try to we also try to see the situation at the core mantle boundary, and we can see that it's very similar to the SAA. But instead, the WPA is also has some reversal flux patch, and the SAA is also influenced by the reversal flux patch below it. And here, we can see better in this time longitude plot. And here we can see that the longitude movement of the core mantle boundary reversal flux patch is very similar to the WPA minima. And here we can see that the red part is the reversal flux patch, and it's this in this figure is this one in the red circle, in the yellow circle. And the gray point is the secondary minima. It's this minima. So we can see that they are almost the overlap. So it again suggests that the reversal flux patch on the CMB are strongly affect the evolution of the WPA. And we also focus on the inclination and the declination. We find that around 1780 years, and especially in the declination, we find that they show the transition from the negative to the positive. And we suggest that this kind of change is also influenced by the reversal flux patch within the local Pacific region. Okay, so now it's time to do some summarize of this work. So we summarized the evolution of the WPA as a 3 different phase. And the first phase is the rapid expansion phase. So in this stage, the WPA center appeared and drifted to the westward, and the area expanded and elongated. And the second phase, we call that the splitting phase, and we think that this one is the very important phase. So in this stage, the most important characteristic is the secondary minima appeared, and at the end of this phase, the area split to two different isolated area. And the last phase, we call it as the diminishing phase. So the old minima repeatedly drifted to the westward and disappeared, and the new one continued its evolution. And we think that this three-phase evolution is very similar to the evolution of the recent SAA over the past 100 years. Because here we can see that during the last century, the SAA, show its rapid weakening and the expansion. So we think that if we follow the 3 evolution phase of the WPA, it's appeared that the SAA has already undergone rapid weakening and expansion phase over the last century. And but now the SAA is maybe in its earlier splitting phase, and during this stage, the SAA is expected to the further expanded, and especially near the secondary minima. But how about the future? According to the SAA's three phase, the SAA maybe will enter the diminishing phase, and maybe as the primary part will diminishing, and the secondary part will continue to expand more rapidly. So our result already show that the recent SAA already get into a very key stage or very important stage of its evolution, and now just because of this, that's why we have to improve the characterization of the SAA. So let's go back to the recent evolution of the SAA. Here, as we mentioned earlier, the splitting of SAA already shows two different local minima. So that means the global minima, the old method, the global minima is no longer enough to describe the feature of the SAA. So we need to use the local minima to better describe its evolution. And for the area, we have the most research have only focused on the overall expansion of the SAA area, but with the appearance of the new local minima, we how to focus on more detail inside this area. And another question is how to calculate the sub area inside the SAA, and the sub area belong to different minima. So, how can we really define and really calculate them? So, in my recent work, I try to define a new simple method. So, by calculating this method is by calculating the partial derivatives, and we can define the extrema and the saddle point in the map. And the first, as we show in this map, we find the point. As we show in this map, there is a 4 spatial point here. And how can we find this 4 point? Where is this location? And we try to find where can mix the first order partial derivative equals 0. That means in the figure B and C, and we have to find the point. How can it this 4 point both in the white part in figure B and figure C? And in this way, we can get these 4 spatial points. And then we should figure out which one is a saddle point and which one is the extrema point. So we plot this 4-point location on the second derivative maps. In the figure D, we can see that all of the extrema point are located at the positive value, and the saddle point are located at the negative value. So after this method, we can find where is the extrema point and where is the saddle point. The saddle point is very important to define the subregion of the WPA. The sub area. Yes. And we try to apply this method to the surface intensity map, and we can see that the DFD theta equals 0 counter is shown as a solid black line, and the DFD phi equals 0 counter is shown as a dashed black line in this figure. And all of the cross point of these lines are classified in the figure below, and the extrema point are marked by the triangles, and the saddle point are marked by the black dot. So after we already find the saddle point, and then we try to use the saddle point to calculate the subregions. So first we try to define the SAA total area as 32 microtesla times F aught. The F aught is a normalization value. And then we use the intensity of the saddle point to try to calculate the boundary of the subregion. So as the green dashed line show in this figure, we use the subregion in the dashed line, and we calculate the center of mass in these two regions. And then we also use these two regions to divide the total area of the SAA. And then I will show some result of my new work. So by using this method, we can find some new feature in this evolution of the anomaly. So this is the full snapshot, and we can see that the df d phi equals 0 and df d theta equals 0 counters are crossed in the 2010 map. And the saddle point and a new minima appeared after this time. So this or we say that this method show a very new vision of the appear of the saddle of the new local minima. And this is for point. And then for the region, for the area, so in the whole region, we can find that only in the South Atlantic part, in the right area, they show some significant change in the contours, and the other part are the lines. Every line are stable; they never show any change. But inside this region, they show very significant change. And this change are mainly caused by the df d phi equals 0 counters. And then here we show some time dependence result of the SAA. Here we focus on the intensity of the minima. We say that the both of these two minima are the intensity of both minima are decreasing, but the new local minima is twice faster than the old one. And for the area, we think that the area's result is the most interesting result in our recent work. So here we can see that the total area, the green line, the total area shows a very straight expanding. But we focus on the sub area. This two sub area is belong to two different minima, and we can see that the two minima is one is the area of the new minima is expanding, and the primary minima is shrinking. The area of the primary minima is shrinking, and they show some anti-correlation shape here. And the minima is also show the westward drift and the wake drift in latitude. And then focus on the location of the minima, the center of mass. The longitude is between these two minima, but the latitude is at the northern of minima. So we think this effects come from the northern part of this area, is this part. So then we try to focus on go back to the long-term characteristic of the contours. So here, please imagine a pure axial dipole field. So in a pure axial dipole field, the dfd theta equals 0 contour would only lie on the equator. But here in these two figures, we can see that these two figures come from the Hist-Carmack model. It's over the past 1,000 years. So here the contours clearly deviate from the equator to the high latitude. So here we call this deviation from the dipole field as a kind of non-dipole feature. And from this figure, we also find some hemispherical asymmetry in its feature by compare with the width of the contours at the different longitude. We can see that the Atlantic hemisphere shows a much larger deviation from than the Pacific part. And in the figure at the bottom, and we can see that at the southern hemisphere, the contours deviation are farther from the equator than the northern hemisphere. So this result shows that the non-dipole features are stronger in the Atlantic and hemisphere and the southern hemisphere. And here we also show some non-dipole feature about of the df phi equals 0 contours. So here we focus on these two blank regions we can see here, and they also show some non-dipole features. And the location of these two blank regions are shows as the order 2 signature. We think that it's related to the order 2 in mental tomographic. And we think this order 2 feature is also caused by the heat flux pattern on the CMB because they all have the order 2 signature. Okay, so then it's a summarize of my work. Here in my work, we describe the evolution of the small-scale weak intensity anomaly, and we called it as a West Pacific Anomaly. It's a WPA, and the WPA has a 3 evolution stage. It's a rapid expansion phase, the splitting phase, and the diminish phase, and these 3 phases show some similarity to the century evolution of the SAA. And for the central SAA evolution, it shows that the rapid local change inside the SAA and near the South Africa part, with the appearance of the new local minima and the sub area expansion and but the primary part area sub area are shrinking. And for the area, we think that the two subregions show very interesting anti-relationship. And for the long-term time dependence, the counter distribution also shows that shows some non-dipole features. And for the DFD theta equals 0 counters, they show that the hemispherical asymmetry and I mean that in the DFD theta equals 0 counter, they show that the Atlantic hemisphere and the southern hemisphere has a stronger non-dipole characteristic. And for the DFD phi equals 0 counter, this shows very important order 2 signature. And the order 2 signature, we think that it's caused by the thermal topological on the CMB. Okay, that is my work. So thank you for everyone.
Thank you.
Thank you.
Thank you, Yaochen. Very nice presentation. Thank you very much. Now it's time for questions. If anybody has questions, please raise your hand, or you can type it in the chat as well. Richard.
Hello, Yaochen.
Raise your hand from the UK.
Hello.
I can see you.
Can you see me?
Yes.
Yeah. Sorry for you, but you have to cope with it. So very nice talk.
Thank you.
Couple of questions, and maybe start off with a concern. You were analyzing the appearance of the anomaly in kind of 1600s from GeoFM or similar kind of things. And
Yes.
the data distribution is such that it's really limited in the Pacific for those times. So I would be very careful about the appearance of something not being a result of the appearance of data starting to be available, because Western Europeans didn't do that much measurement of the magnetic field in 1600 in the Pacific. So you want to be a little bit careful on comparing with the data distribution for GeoFM, say. If you start putting in archaeomagnetic, maybe it's a bit better, but it's still a little bit worrying that there is a very large variation in number of data for that region over that time.
Yes, thank you for this suggestion, because we also think about this problem during this work, and we try to show all of the Navy's ships log distribution, and we find that actually they also have some distributions in the West Pacific part and the South Atlantic part during this time. But the problem is they don't have much, they don't have many in-density records before the 18th, 19th centuries. So
well, really, I would say it's probably the inclination you really need. The intensity is a bit kind of random.
Yes.
So if you've got some inclinations, obviously that could tell you a lot, but I'm not quite sure that you do. 1620 is a scarily early time. It's a way to say, okay, this is possible, but I wouldn't draw anything more from that than that.
Yes, thank you for this suggestion. And we also think about that. So we choose these two models to try to show the story of the WPA. So we also consider the histochromark this model. And because this model, they combine some magnetic field data. And these two models in this figure are both of the model shows the pair, maybe it's not the appearance, but they also show the WPA during this time. It's not only in the histochromark the WPA appeared earlier than the result in the GeoFM1. But they also show
that's an encouraging result, curiously, because the two models saying the same thing, if they're using more or less the same data, doesn't really tell us anything. But if there is extra data going in, that's fine.
Okay.
Yes, I would be a little bit careful. So, second point, which I'm sure you're aware of, and you've been talking with your team as well. When you're looking at the surface intensity, surface anomalies, it's all very nice, but it's obviously a result of upward continuation. It's a geometric effect. So I think a little bit more, I'd like to see a little bit more digging into what's happening in the Pacific Anomaly near the CMB to see if there's any physics in it. Because until we look at the field at the CMB, then we don't really have any physics.
Yes.
So just talking about the surface and the evolution of the anomaly is interesting geometrically, but it doesn't necessarily give us that much causal information, again, because of the upward continuation. Right, my third point, sorry, I've been talking too much. And Sanya, please interrupt me and shout over me if I start talking rubbish, because I'm going to be talking about your stuff here. So the group at the Potsdam group have been looking at the field for the past 100,000 years, and they've seen the appearance and disappearance of the South Atlantic Anomaly, but less so anything else. So if you look at those records, that models, say those models, do you see any appearance and disappearance of your Western Pacific anomaly?
Around the 5,000 years ago, you mean? I'm sorry?
In the last 100,000 years. So you could see from the one which I woke up on it was the Brown et al. Paper, which I was involved with, where you could see a South Atlantic anomaly appearing about 48,000 years before, and then disappearing, and then the
appeared.
Then the excursion happened, which was different. So you could, but there's a bunch of those other things. And Sanya, if you could, if I start, I'm talking rubbish. There's about 5 or 6 of them where it appears and disappears. Do you see anything similar for your Western Pacific anomaly that you've identified?
Yes.
Sanya's appeared.
Yes, sorry. No, short answer, no, we haven't looked systematically for other anomalies, but I do believe they are. even for the South Atlantic. It's just a snapshot we look at and it appears disappear, not related to excursions.
Okay, but the thing about it is, I would recommend you have a look for the Pacific one as well. And seeing I've managed to force Sanya into the call, maybe you can talk to her about it, getting extra information if you need to know what to do about it. There, that's mean of me. Right, I'll run away now. Thank you very much. A very nice talk.
Thank you so much. I also know some work they try to find the archaeomagnetic records from the southern China or Japan, and they find the records as with a very low intensity in 1100 year and in the 14th centuries, and they also show that they has the very low intensity in the Pacific region. So I'm not sure it's like a rapid WPA or something, but it's a good result for the West Pacific Anomaly. Yes.
Thank you. Thank you for all the
Thank you so much.
questions as well, and the ready answers you had. Well done.
Thank you so much. Thank you, everyone.
Are there other questions?
Can I talk? Can I talk?
Oh,
We are from
of
Japan.
course. Boya-san.
Yeah.
Good night. Good afternoon.
Good night. Good night.
Good night. Good night.
Night. It's really night. Anyway, in this area, the Siberian anomaly is kind of a dominant part of the anomaly, I believe. Do you have some relationship between this anomaly and the Siberian anomaly?
The West Pacific anomaly and
Yeah.
which anomaly? I'm sorry.
Siberian anomaly. To western part of Eurasia, there is a very strong anomaly staying for 2,000 years, 4,000 years. I don't know. I'm not sure. So I couldn't see that in your diagram. So I was a little bit curious. What's the difference?
So for the West Pacific anomaly, it's we only talk about the past 400 years evolution, and actually it's only appeared during 200 years. Yes, and in this almost 100 years, it's already finished the expansion and to the diminish all of these surfaces. And I'm sorry that your question is about the relation from the West Pacific, from the WPA to SAA, or from the WPA to the more ancient one.
Siberian anomaly still strong, I believe. In Siberia.
It's the northern strong anomaly.
Yeah.
I don't think they have some relation between the high latitude strong anomaly and with this one, because we think about that the West Pacific anomaly, it's impact on the reversal flux patch on the CMB. So we think maybe it's a different impact.
Okay, thank you very much. Nice talk.
Thank you so much.
Thank you, Shibuya-san. Are there any other questions? It's very late now in China.
No, it's okay. I'm very happy to give this presentation, but actually I'm a little nervous, but yes, I enjoy it. Yeah.
You did great. Thank you very much.
Thank you so much.
If there are no other questions from the audience, okay, everybody's clapping.
Thank you, everyone.
Thank you, thank you. I will just share my screen again.
Okay, so I stop.
Yeah, okay. So thanks again, Yaochen, and I want to just remind everybody that these talks and the previous one are gonna be on YouTube, recorded and referred to ERDA, and we are gonna present some of these numbers and results in terms of views and achievement in the past 6 years, 7 years of activities at the EGU conference. So if somebody is there, please come over. So thank you very much.